A parametric surface is a generalization of the notion of curve, but now the domain is including R2. So if we have a system of coordinates, this surface S is given by a parametrization where each of the components in R3 depends on two variables now. So it's like an image of some piece of R2. So the parametric equations of this surface are going to be given by x equals the first component, y equals this, and z equals this. Each of these functions depending on two variables, and these variables depending in some particular range describing the domain D. Let's sketch the surface given by these parametric equations. This is an alternative way to say R of UB is equal to V. And this is the description of the domain D. In order to draw a sketch of this curve, observe that the description here corresponds to the description of a circle of radius 5. We observe here that the variation of xy describes a circle. We're going to have a circle in the xy plane. And the z component is just given by the equation v, where v vary between -1 and 1. So it's going to have any value here between -1 and 1. So that will be a cylinder like this. So this surface here of this cylinder is the one described by these parametric equations with this variation of the variables in D. At each point of the surface, once that we have a surface like this, we have a point in the surface, and at each point we can define what is the tangent plane at the point. In order to do this, we need first the parametrization of the surface S, the given point where we want to calculate the tangent plane, and we are going to calculate what we are going to call RURV. This is going to be the vector of the derivatives of each of the components of the parametrization, in this case with respect to u, and in this case with respect to b. So these vectors are going to be very important to determine the normal vector to the surface, the normal vector to the tangent plane. So this normal vector, let's call it n, the normal vector here, this normal vector is going to be given by this vector evaluate at the point P, and this vector evaluate at the point P2, and doing the cross product between them. Remember that the cross product between two vectors gives a vector that is perpendicular to both. Okay, so that's the way to calculate the vector, the normal vector. Let's call ABC the components that we get by this calculation. And then the tangent plane to the surface is going to be given by ABC, I mean the components of the normal vector, and here we're going to put x minus the component of the point where we want to calculate the tangent plane. Okay, so this then will be the equation of the tangent plane at the point x0, y0, z0 with normal vector ABC calculated by the cross product between the derivatives respect to u and respect to b. Let's calculate the tangent vector to the surface given by this parametrization at the point 414. Okay, so let's start by calculating everything that we need for this, essentially the normal vector. For that, let's start by calculating RU, that will be the derivative respect to U of each of the components here. So U squared, the derivative respect to U is 2U. Here, the derivative respect to U is 0, since there is no U. And here, the derivative respect to U is just 1. Let's do the same respect to V. Derivative of this respect to V is 0. Derivative here respect to V is 2V, and here respect to V is 2. Then we calculate now the normal vector as the cross product of these two, RU cross RV. As you know, this is the determinant where we put in the first row I, j, k, and in the second row each of the vectors that we are doing the cross product. So in this case, the vectors are 2u, 0, 1, and 0, 2v, 2. So this determinant will give us the normal vector. So let's start. The first one will be doing I multiplied by this vector, that is 0 minus this. So this is I times just minus 2b. Minus j, we eliminate this and this, will be this times this minus 0. So that will be j times 4u. Plus k, we eliminate this, will be just this minus 0. So this is then 4ub. So the normal vector is minus 2b minus 4u and 4ub. So this is the normal vector in general. Now we need to evaluate at the point P, that in this case is 4, 1, 4. So the normal vector, the ABC, then will be evaluated at 4, 1, 4. Observe that the point P4, 1, 4 corresponds, this is u squared equal 4, so this corresponds to u equal 2 and v equals 1. And so when we plug in these values of u and v here, we get that this is minus 2 times 1, which is minus 2, and minus 4 times u, which is minus 8, and 4ub, which is 8. So we got the normal vector, and we have also the point. So the normal vector and the point is all what we need to write the equation of the tangent plane, which will be a, which in this case is minus 2x minus the first component here, that would be 4, minus 8, y minus the second component, that will be 1, plus a, z minus the third component, that will be 4, equals 0. So we do the distributive here, so we multiply everything, and we get that this is minus 2x. We combine like terms. The numbers are going to be here, will be minus 8 plus 8 minus 34, so we're going to have in the other side 16. And so simplifying here between 2, that will be minus x minus 4y plus 4z equals 8. So this is the tangent plane, so to this surface at this point. Now the surface area, so if we have given a surface like before over certain part here, certain domain, we have this surface area here, so the value of the surface area is going to be given by the double integral over the domain that we want to calculate the surface area on, of the norm of the normal vector. So the normal vector that we calculated before as a cross product between RU and RV, then we need to calculate the the norm. The double integral of the norm of that vector over the domain is what will be the surface area. So, for instance, we have the surface in this case defined by these parametric equations, and this is the domain D over which we want to calculate the surface area. Well, in order to calculate the surface area, as before, we need to start by calculating the vectors RU and RV. So the vector RU will be the derivative of each component here respect to u. In this case, the derivative of this respect to u, this will be constant, will be out of the integral for sine b, and the derivative of cosine of u, that will be minus sine u, comma, the derivative here respect to u will be for sine b, that is a constant, out, times the derivative of sine of u, which is cosine of u. And the derivative of this respect to u is 0, since there is no u there. So we do the same for the derivative respect to v of each one. Here, derivative respect to v will be 4 cosine u, and then the derivative of sine of b, which is cosine b. And the derivative respect to b here will be 4 sine u, that is a constant that goes out, times the derivative of sine of v, which is cosine of b. And the derivative of this respect to b will be 4 minus sine of b. So we have the two derivatives. We're going to now calculate n as the cross product of these two. We're going to write in the first row I, j, k, and so in the second one, this vector, and this equals I times, eliminating this and doing this determinant will be just this product. In this case, the other is 0, so this is minus 16 sine square of v cosine of u. And then minus j, we eliminate this times this, the other one is 0. Sine of u, sine square of b. And plus k, when we eliminate this, we have this minus this. So simplifying, this will be the vector minus 16 sine square of b cosine of u minus 16 sine u sine square of b. And then simplifying here, we observe that there is a common minus 16, also sine of b is also common, and cosine of b is also common. So taking all that as a common factor, we get that this is minus 16 sine v cosine v, and inside remains sine square plus cosine square, that is just 1, right? So we just don't need to write down. This will be then the normal vector. So to calculate the integral now, we need to calculate the norm first. So the norm of this vector will be the square root of, so we're going to put here the additions of the squares of each component. (16 squared) as well as sine square of b is common in the three terms. We are going to take it out of the square root. So the root of 16 squared is going to be 16, and the root of sine squared is going to be just sine. And so inside of the root remains, once that we took sine squared, here remains the other sine squared, cosine squared, plus once that we took sine squared, remains here sine squared u, sine squared b. And here remains just this. Sine square of b is common. We can take it out, so that will be this. And inside of the root, we have here sine square of b common. But when we see what remains, here is cosine square plus sine square of u, which is 1. And then we have plus cosine square of b. So at the end of the day, we have, this is just a 1, so we have just sine square plus cosine square, which is 1. 1, so at the end of the day, this is just 16 sine v. So this is then the norm of n. So this is what we need to integrate. So if you remember the formula that we saw before for the area of a surface, so we need to integrate just the norm of this vector. So we got that the norm of this vector is 16v, so that's what we are going to integrate. So the surface area is going to be the integral over d, which in this case is going to be this variation here. So it's going to be 0 and 2 pi. This is going to be the variation of u, and the integral between 0 and pi thirds, this is going to be the variation of v. And the function that we have to integrate is the norm of the cross product that we just calculate, and is 16 sine of b. Okay, so now we integrate this. The 16 is going to be out, and the integral of sine is going to be minus cosine. So this is 16 integral between 0 and 2 pi du, and so inside here we integrate sine of v, which is minus cosine of v, and this is going to be evaluated between 0 and pi thirds. So we can take the minus out, so this will be minus 16, the integral between 0 and 2 pi of cosine of pi thirds. So cosine of pi thirds is just 1/2 minus cosine of 0, which is 1. And so this is du. So 1/2 minus 1 is minus 1/2. So we're going to have outside 16 over 2. And so the integral of 1 is just u evaluated between 0 and 2 pi. 8 times 2 pi. So the result is 16 pi. Observe that the surface, the parametrization of the surface coincides with the spherical coordinate that describes exactly a sphere of radius 4. So we have, this one is 4 here, we have a sphere of radius 4. And so what we are calculating is this in this domain where the u goes between 0 and 2 pi. So we get that this goes all the way around, so all around the whole sphere. And v vary between 0 and pi thirds. So we have that is the surface until here. So we are calculating then the surface area of this cup, just this upper part of the sphere.